First of all, I would like to thank the organizers for giving me a slot to give a talk at String Pheno series. So this presentation is based on the recent paper with David Andriot, where we try to understand if the potential gets modified due to backreaction of local objects. So I will start with a general introduction, then I will explain the methodology, and in the last 5 pages, I will present to you the results. So in string phenomenology, one of the main goals is to find a solution, like from string theory, that is able to describe the evolution of the universe and the standard model as well. So a very essential starting point is the construction of vacua. And in our context, what do we mean by vacua? We start from a theory with extra dimensions, like more than 4 dimensions. We perform the dimension reduction, we compactify it, and then we minimize the potential. And the potential, the minimum of the potential is going to be analogous to the cosmological constant. However, as you may know, it's very hard to find de Sitter in string theory. I mean, so far we have not constructed a single consistent solution. For this reason, we turn our interest and we are looking for other maximally symmetric spaces. So we would like to see if, for example, it's possible to find AdS solutions where all the moduli are stabilized, the fluxes are quantized, and if it's possible to hide extra dimensions. I mean, for this property, we use the so-called scale separation criterion that I will show you in short. So there is a parameter space that people tend to work with, since it's easier to understand and it's more economical in terms of ingredients, which is called the classical limit. In this classical limit, string theory is described by 10D supergravities, and in order our solution to belong to this parameter space, we want the coupling, like the dilaton, the 10 dilaton, to be very small, and also the length scales to be way larger compared to the string scale, such that we neglect and we suppress stringy effects. What do we mean by scale separation? I mean, we will not use scale separation in this presentation. However, the title includes scale separation. It's one of the striking properties of the model that we're gonna talk about. So a qualitative condition to estimate whether there is a large gap between extra dimensional states and the vacuum of the EFT is to ask the KK scale to be decoupled from the curvature radius for example, of the AdS. So we will focus on a specific model, which is called DGKT. We get this model from 10-dimensional massive type 2A supergravity when we compactify on a specific orbifold, like an orbifolded T6 torus, actually. And what we get, the EFT, is a 4-dimensional AdS n=1 supergravity, which possess all the properties that I told before, like quantized fluxes, full moduli stabilization, scale separation. So there is like a technical characteristic in this model, but also to the most of the other models that I mentioned here before. All of them, they come from type 2A, from massive type 2A, with smeared O-planes. So this is not actually a solution of 10D supergravity. It's an approximation. And there's been a lot of criticism on if those models are reliable and viable string theory solutions. And other people have tried to understand what happens when you combine the Romance mass and smeared O-planes if there is like a string theory uplift or not. So apart from those difficulties and these technicalities, let's say, there are also swampland conjectures that they really disfavor the presence of their existence. I mean, there are conjectures like the strong AdS conjecture, distance conjecture, which says that models with such characteristics, they should not have scale separation. So is DGKT a counterexample to this conjecture, or something is going wrong due to the approximation, like to the smearing approximation that I will talk in short? Let's see, what do we mean by smearing approximation? Like in string theory, we have objects that they fill some space, like some direction of the 10D space, and they're localized to the rest of the directions. And the localization is described by singular functions, by delta functions actually. So if you take, for example, the action of O6 plane and you embed it in the 10D space, you need a function in order to describe it. And the same happens when you try to derive the equations of motion, the so-called Bianchi identities. There are delta functions that appear. So in DGKT, but also in other compactifications, it's very common to replace the singular function with a regular function. And I borrowed this picture from Thomas Hello's talk, which shows how the local sources are distributed globally over the cycles, instead of being locally distributed. How does this affect our setup, this approximation? This affects the dilaton and the warp factor, and also the deformations of the internal space, because the dependence on the internal coordinates becomes really weak, and you can consider it to be constant. So this is like an important simplification when you smear the sources. Also, your fluxes become harmonic, and yes, of course, your internal space is Ricci flat. So then you ignore the backreaction from the local objects, and you don't get the exact profile of your fields. People have tried to understand if this approximation can be trusted or not. However, I want to ask the general question: if we had a complete solution for DGKT, would this change the results, like the properties of DGKT? For example, how would the potential will change? How would the masses? How would the masses change? Actually, we don't have the complete solution for DGKT. That's why we perform the approximation, because we cannot solve the exact system. However, we do have a method where we can approach, let's say, the exact solution, or unsmear, like go beyond smearing. And this method was proposed by Daniel Junghans a few years ago. The method is the following. In DGKT, as I'll show you, there is a free parameter, an unbounded parameter, which is related to a flux, to a F4 flux. All the quantities in DGKT, like fields and fluxes, can be expressed in terms of this parameter to some power. And then you can say that I perform the 1/n expansion, and the zeroth or the smeared order of my fields describe DGKT, describe the fields in DGKT, while the next order complete the solution, the next order to smeared solution. Here, for example, imagine that phi stands for the dilaton, and F is like a flux. These are the fields contained in DGKT, while those are corrections to those fields. And of course, for large values of n, those corrections are subleading to the zeroth order fields. As you can see here, for example, in the dilaton expansion, the first order, the next to leading order, contains y dependence. So this internal coordinate dependence will catch the back reaction that we get from the sources. I mean, also other people with using different methods like have tried to find and calculate the back reaction of the sources. I would like to inform you that unfortunately this paper contains a lot of technical details, and I will present several formulas. However, like these formulas are Einstein equations and just work potentials, not more than that. So let's see DGKT, and let's start from some more generalized ansatz. So we consider a world space of this form, and we start from massive type 2A. We perform the dimension reduction, and the potential that we get, the 4D potential, has this form. Of course, the first line contains derivatives with respect to internal coordinates. This means that in DGKT setup, where it's smeared, and for example, the word factor, the internal metric is Ricci flat, and the dilaton, they do not depend strongly on the internal coordinates. The first line vanishes. And the second line, if you plug in the flux ansatz that we have here, it gives you back exactly DGKT. Another characteristic of this model is the cancellation, is the tadpole cancellation, which happens here just with smeared O6 planes. So you can cancel the tadpole, and the fluxes, the H3 and the Romance mass, get bounded. The free parameter that I told you before, that it exists and it can let you perform this expansion, but not just only this expansion. This is also like you achieve large volume and scale separation due to the freedom on the F4 flux. Is this one. So it's F4 is the flux of F4, and the parameter is n, and you consider it to be like integer and then discretized. It's unbounded by Bianchi identities. I mean, the Bianchi identities vanish trivially for F4, so it's free, and you can take it to be extremely large. So one can write down the smeared equations of motion. Can solve the equations of motion, and of course get the same results as minimizing the scalar potential. And let's talk a bit about the scaling, because it plays like a crucial role here. So if I assume that this is the scaling, like this, like my fluxes and my fields have like an arbitrary scaling, an unfixed scaling. Those scalings here are fixed by the tadpole condition. You plug these ansatz in the equations of motion, and you require the terms to scale the same way. You get back a specific scaling for your fields and fluxes. Why I emphasize this? Because this scaling seems to be unique. So here, actually, we have re-expressed the scaling of the dilaton and the internal volume deformations in terms of the flux, the F4 flux parameter. However, when we go next to leading order and we perform the expansion, it's not clear what the scaling is. So there's going to be some freedom that we are going to use to our advantage. We perform the detailed balance analysis, we find the scaling, and then we re-express like the volume in terms of the scaling, the coupling, and the scale separation condition. And what we see is that when we take large values for n, we go to large volume with coupling and the scale separated regime. So let's go beyond the smeared solution. As we said, we expand our fields and our fluxes in an n1 over n expansion, where the next to leading order is subdominant to the leading order, to the smeared order. So one can go to the full equations of motion derived like from a massive type 2A supergravity and plug in these answers. What we'll get back is the following. He will get back the smeared equations of motion and a set of equations of motion that include corrections to the fields. For example, here, this derivative is with respect to the internal coordinates. And since the dilaton depends now, the correction to the dilaton depends on the internal coordinates, you get correction actually to your smeared equations. And we ask, this system of equation actually can be solvable. I mean, if you consider the dilaton equation and the Einstein equations, you can solve it, and you actually find the profile, the corrections to the constant profile of the dilaton, of your F2 flux, and of your warp factor, and of your metric. I will show you this, but I will not go into detail. And the question is the following: what happens if you put these corrections into your potential, or if you go back to your warped potential here and perform the expansion, but now considering the corrections that you have found from the equations of motion? Before I do this, let me show you something. So this is the full expansion that it was considered in paper of Junghans. So the metric is expanded in a specific way, the warp factor is expanded in a specific way, the dilaton and the fluxes. However, here we let some freedom to the scaling of the corrections of the fluxes. We can have this freedom because if somebody writes down the equations of motion, the corrected equations of motion, we'll notice that the corrections to the fluxes, the F1, for example, correction, do not appear. So they do appear at some other subdominant order. So we do have this freedom, and we will use it. We'll try to use it, actually. Another requirement that we want for our setup is the fluxes to be harmonic. I mean, the forms to be harmonic. We can see this from the Bianchi identities or from the flux equations, okay? Because we want the exterior derivative on a harmonic form and the Holtz dual to this harmonic form to vanish. So what we require is that the first terms of these equations are dominant to the other terms. So when they are dominant, you can see them as like a single equation for large values of n. So the F41, for example, is can be equal to 0 for large values of n. You get some interesting inequalities from this requirement, but we will not go into much detail. So let me go back to the potential and let me use the corrections that Junghans found in his paper. So the correction to the metric, the dilaton, and the warp factor, as well as the correction to F2, have the following form. As you can see, they have like a 1 over r form, and where r is the distance from loci, like from a locus of your O6 plane. So when you approach, when you're far from it, you can forget about this term. This becomes negligible, and the constant profile that those terms have is dominant. So we go back to the warp potential. We plug in those corrections, and we find that indeed there are some terms that are related to the corrections to the Ricci scalar, derivatives on the warp factor, and this term which comes from the tadpole cancellation, from the Bianchi identity actually. However, those terms make up total derivatives and vanish. So we were able to find and see the back reaction at 10D equation level, but when you perform your expansion in your warped EFT, those terms vanishes and you don't see the effect of back reaction. But we should not get disappointed, because in the potential there are also fluxes, and somebody can perform the expansion on the fluxes. We see that the dominant contribution that comes from this expansion comes from the flux term. Like if you if you consider one corrected flux, for example, this dominates over the other terms. And you see that the scaling is subdominant to the smeared potential. This means that for large values of n, this can be considered to be negligible. So the corrections to our potential has the following form. This is the smeared solution, the DGKT solution that is dominant, and this is the correction due to fluxes, which is subdominant. Okay, so here we have corrected H31 and F41, and the contribution that we get from the O6 planes. So what happens with F21, for which we had an explicit solution? If somebody puts down the hierarchy due to scaling, we see the following. Here we have DGKT with scales like this. So we have alpha prime corrections that we know that at some point alpha prime corrections will kick in and they will modify the potential and the masses. However, if one considers the scaling in Johans, we'll see that the corrections due to the fluxes appear at the same level as alpha prime corrections. But as I told you before, we have some freedom on the scaling, so we can go and change the scaling of our fluxes and put these corrections here. And then we go, we minimize our potential. And this way we hope to find corrections which modify the smeared solution. The F21, the correction which is relevant to F21 is very subdominant, and also other terms like derivatives on the warp factor and the dilaton are very subdominant at this level below alpha prime correction. So there is no point to consider those corrections if you don't know alpha prime corrections. Okay, so a few slides before, we required our forms to be harmonic. And we want to check what happens with flux quantization in this case. So the corrections, okay, we knew that the smeared fluxes were harmonic, but we also required the correct fluxes to be harmonic, and this means that they will fill the same cycles. We go and perform the quantization. Okay, so this is the smeared flux, and this is the correction where we have also this freedom for the scaling. Still, the nominator the exponent of this term remains positive. However, if somebody goes to check the flux quantization for H3, we'll notice the following. The smeared flux scales like n to 0. This means that this is 1, and 1 is the smallest integer that we have. So the correction has to be 0. Okay, I mean, since the correction is going to should be subdominant to the smeared flux, this has to be 0. And somebody can see this from the from DGKT. You can go to DGKT, perform the tadpole cancellation, and see that H3 gets the value 1. So this has to be 0. So since the flux is 0, we conclude that the correction to H3 is 0. H31 is 0. But okay, we still have F41 where we can put it above alpha prime corrections. But as I told you before, we were not able to see the F41 and H31 in the next two leading order equations. We can go and push it a bit further and consider next to leading order equations of motion. What we see is the following: that in this equation, for example, there are no other terms involved. There are not like derivatives on warp factors. There are no derivatives on the dilaton. They're just fluxes. And as what we argued before with the the quantization of H3, but the correction to H3 is equal to 1. So this term vanishes, and there are those two terms that have to vanish. Okay. What we find actually is that if you try to solve this equation, the correction to F4 flux vanishes as well. So we expected to find some corrections here due to fluxes, and we find out that they're 0. So there is nothing in between here, the smeared potential and the alpha prime corrections, because the corrections that come from derivatives on dilaton and the warp factor are very subdominant. Okay, somebody can see this also from the EFT perspective. Somebody can go and extend it and include also axions, because so far we included the F2 and F4 and we neglected the rest of the terms. So one can also include F6 and get the potential. And what we'll see is that the axionic terms that appear, the corrections actually due to axions, they're either subleading to alpha prime corrections, or they're at the same level of alpha prime corrections. There's still F6, which is a bit tricky, but it's still under control. So if you get the EFT and you minimize it, you still find that your F41 has to be 0. And that's all. What we wanted to see was we wanted to study whether corrections due to backreaction effect backreaction affect scalar potential. We imposed scaling conditions to have like harmonic H3 and F4 fluxes, since we realized that the corrections that come from the warp factor and the dilaton, they become total derivatives and they vanish. And then we imposed a quantization condition, and we argued that the correction to H3 has to vanish. We pushed it further to an NLO, equation of motion, and we showed that also the corrections to F4 flux vanishes as well, while the rest of the corrections that come from F2 and derivatives on two warp factors or two dilatons, they're very subdominant to alpha prime corrections. So unsmearing DGKT seems not to affect the potential above alpha prime corrections. Thank you.
Thank you very much, George. We have a couple of minutes for questions because we were late today. So are there questions?
Yeah, I have a question.
Okay, so Vincent, you can start.
Yeah, so I'm a bit confused that you say that the corrections of F2 are very subleading.
Yes.
Because F2 has to solve the Bianchi identity with the O6 planes that are local. So I would say that they encode the local information that is crucial for well, the localization to make well, to make sense. So I'm a bit confused.
Yeah, I mean, yeah. So let me show you. In the scalar potential, for example, we argued that the next two leading order corrections due to fluxes come from like one corrected flux. So here we have two fluxes and you correct one flux. If you do this for F2, in the answers that we have in DGKT, F2 0 is 0. So this term will vanish. And you have
you mean, okay.
Yes.
Okay.
So,
you mean
the next term,
F2 ones.
Exactly. So you need
okay,
F21, which is a very subleading.
Okay. Thank you.
Era, go ahead.
Okay, I just have a quick question. Thank you for the nice talk. Yeah, did I understand correctly that what comes in at higher order? I mean, what is more dominant, alpha prime corrections or the corrections to the DGKT solution at next order in the flux parameter? That's what.
Can you repeat? I mean, what are the
three level solution, and then there's a correction in this expansion of the flux parameter?
Yes.
And are those corrections bigger or smaller than the alpha prime corrections?
We wanted to make them bigger than alpha prime corrections because we do have this freedom on the scaling. But when we pushed to next to leading order, or when we consider flux quantization, we realized that the corrections to the fluxes to F41 and H31 are 0.
But the DGKT solution has corrections, like if you go back to like right at the beginning, you were saying there's corrections like one of, if that slide is
Yes.
yes. Two more, or even here, like you have an expansion in N, right?
Yes.
And so you have the tree level solution, and then you have a next leading correction.
Yes, the tree level solution is fixed. Tree level solution is fixed.
But the next leading correction,
The next
bigger or smaller than the alpha prime corrections?
We don't know because we have this scaling freedom. You can ask them to be above alpha prime correction or below alpha prime correction because you have this freedom. But
but the scaling, if you change the scaling, you also change the size of the alpha prime corrections because you're changing the
because the expansion that we consider here is independent for each field or flux. So you see that, for example, the metric.
Then the size of the alpha prime corrections doesn't depend on N?
It depends. So, it depends on N, but here, here, we just consider like a, how to say, like a solid manifold, like a solid Calabi-Yau manifold, like in this scale, which is resolved. Sorry. And the scaling of this term that appear due to correction to the curvature is fixed. So we don't correct actually alpha prime corrections. So yes, you can do this. I mean, I have this. We examined this to be honest. Like in this case, if for example you expand your alpha prime corrections, you need
I'm not asking about corrections, alpha prime corrections. I'm just saying it doesn't matter. I think I will look at the paper. I don't want to take up people's time.
Okay.
All right. Thank you for your answers.
Okay, great. Thanks, George. And we can go to the next speaker. We have to move on.